Good morning, my doctors. Can you hear me? Can you hear me, Dr. Henry?
Yes,
I
sir.
can hear you.
Yes, sir.
Okay, good morning, everybody. I hope you had a wonderful night. I want to continue from here, elaborate on the introduction that was given by Dr. Kilade. He introduced us to the physics of MRI. So today I want to elaborate on some of the salient points raised. This will continue in subsequent lectures. So in MRI today, I want to look at some key processes, some key terms in MRI that are very, very fundamental to understanding the physics of MRI. I'm going to share a screen with you, but before then, I want to outline the topics we are going to look at today. Possibly finish them. If not, we continue on Wednesday. So first, we want to look at spin. I hope you can see clearly.
Yes.
I don't want to use the whiteboard or Zoom's whiteboard because it will retard my speed. So we want to look at, we are going to look at spin. We are going to look at alignment and precision. Precession. Thirdly, we are going to look at the principle of resonance, which is actually about the most important of them all, then together with the principle of relaxation. We might go on to look at localization, but I don't think we'll have time for that. So we want to start with spin, but before then, I would like to share a screen with you. So I'm going to use the screen in explaining these parameters, these processes. Okay. I'm sorry. Okay, I thought I opened it up. I'll give you a little time. Okay, let me see. Are we there? Hello?
Yes.
Yes, we
You
can
can
hear
see the
you. We can
screen.
see the screen.
Okay.
Yes.
We can see it.
Yes.
Okay, basically we'll be looking at the physics of MRI. The contents as we have them there, but we are not going to go into some of this content. We'll base our discussion this morning on the physics of MRI, and under these topics, these subtopics I have listed on the board. So I want to look at types of atomic motion. Of course, we are very conversant with how the electron orbits around the nucleus. But our interest today will be how the nucleus and the content of the nucleus are spin on their axis, or the whole, the nuclei, how they spin on their axis. And of course, the nuclei we'll be looking at not that thing, but the protons and the neutrons. For a proton and a neutron, they have a quantum mechanical description we call spin, just like the electron also has a spin. The protons have their spin and the neutrons have their spin. And for protons, for example, if we have a human body, which is composed of so many protons, or basically the proton we are going to be looking at is the hydrogen nuclide, of course, which we depict as a proton. It describes everything we want to talk about a proton, because the hydrogen nucleus just has one proton. That is the normal hydrogen we know, not the other isotopes of hydrogen. So for a hydrogen proton, which I have drawn on the board, a hydrogen proton is a charge. And then this charge moves, revolves. It moves about a particular axis. It is a charge, it revolves around a particular axis. And because of this spinning or revolution or rotation, as the case might be, depending on how the term that will help you get the explanation. As this charge revolves, it is going to induce a magnetic moment. And therefore, from our basic physics, from the law of electromagnetic induction, a moving charge will induce a magnetic field, or will induce a magnetic moment, which actually constitutes a magnetic field. So because of that, we are going to have, from the right-hand rule, we are going to have a spin of. Don't bother yourself about that, because like I told you before, it is a quantum mechanical model. Why the spin is up is just because of the direction this charge is gives to this body because of the rotation. So we are going to have a spin up. And also we might have some protons or even neutrons revolving about an axis and this way anti-clockwise. This one will actually have give us a spin down. So what actually happens in a body? We might we have so many atoms, so many. We have so many elements, of course, comprising of different atoms. There are some atoms that have a particular number of protons and a particular number of neutrons. So the sum of the neutrons and the protons will actually give what we know as a net spin. They all have their various spins. but a combination of all the protons and neutrons in the body will amount to what we know as net spin, a net spin, or the resultant spin, or the cumulative spin, as the case may be. So for a normal object, I mean, for a normal particle, let's take hydrogen, for example. Hydrogen just has one proton. So hydrogen has no problem. And depending on the orientation of the rotation, might be this way, it's going to have spin half. It's going to have spin half. So many other elements also have their own combination of spin. So if the combination of spin, if you have an even number of protons and neutrons, they are going to cancel out. For example, an element that let's take carbon, for example. Carbon has 6 protons and also has 6 neutrons. 6 neutrons, 6 protons, 6 neutrons. So at the end, the spins of the neutrons, the 6 of them, depending on the energy level, but we shouldn't bother ourselves with that. The 6 neutrons their spins will cancel out. 1, 2, 3, 4, 5, 6. Because the first one will be up, another one down, up, down, and so on and so forth. So they are going to cancel out. At the end of the day, for carbon, the net spin will be 0. So elements that have a net spin of 0 are not useful for MRI. But the ones that have spin of multiple of 1, multiple of half, or 1/2, we can have 2 halves, which is 1. We can have 3 halves, which is 1.5, 3/2. We can have 5 halves, as 5 all over 2. These ones are the major focus of nuclear magnetic resonance, which is used for nuclear magnetic spectroscopy and imaging, which is a concern. So hydrogen, which has one spin 1, spin half, is the best a nuclide for magnetic resonance, not just because it has half, because of its abundance and because of the high ratio, the high number of its gyromagnetic ratio. We are going to come to that later. So for spin, any atom or nuclide that has a net spin is the one that we are going to focus during this magnetic resonance. So that explains spin. Spin is just a quantum mechanical explanation for revolving charges. When a charge is revolving about an axis, it's going to induce a magnetic moment. So the magnetic moment is what constitutes a magnetic field. We also remember how electricity is generated. Electricity is generated when magnetism moves about an axis. So vice versa. Electricity can generate magnetism, and magnetism can generate electricity. But for MRI, we are using the revolving electric charge to produce magnetism. So that brings us to the next concept called alignment. Let's see this slide. So like this slide we have, the tendency of an MR active nuclei to align its axis of rotation to an applied magnetic field, blah, 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 is dependent on whether we have odd number of protons or neutrons or both. So hydrogen, carbon 13. Remember here, the carbon I initially used was the carbon 12. That is the stable carbon we have. But for carbon 13, which is a little bit radioactive, has...
we can't see your slide.
We can't see the slide again. Okay. So, sorry.
Yes.
Let me go back. Okay. Let me share. can see it now.
Yes, sir.
Okay. Sorry.
But you need to put it on PowerPoint, sir, to play.
Yeah, no problem. So we are there. So these are the hydrogen, the carbon 13. Carbon 13 now, we now have an odd number of neutron and proton combination. Nitrogen 15, oxygen 17, fluorine 19, sodium 23, phosphorus 31. These are very excellent examples of nuclide we use for MR, nuclear magnetic resonance. So we are going to alignment. When in the absence of an external magnetic field, a very strong external magnetic field, with all the protons, basing my discussion on the hydrogen atom now, all the hydrogen atoms will have various orientation. They will have various orientation about their axis. They will have various orientation. Some will be 20 degree east, 10 degree north, and so on and so forth. They will be randomly orientated in space. But if you now apply a magnetic field, they will now be aligned, either parallel to the field or anti-parallel. In fact, both parallel and anti-parallel alignment of the let me go back to my board. So both parallel and anti-parallel alignments. Like I told you, if you have, we have numerous proton, billions of protons in the body. Some are aligned down and so on and so forth. So they are randomly orientated in space. If you now apply a magnetic field, a strong magnetic field to the body of protons of the nuclide, these nuclides will now choose two orientation space, parallel and anti-parallel. Some of these protons will be aligned parallel to this external magnetic field, while some will be aligned anti-parallel to the magnetic field. So we now have something like this. I will now have some things like this. Some parallel, while we have some anti-parallel. Why do we have this? But from studies, from quantum mechanical studies, and even classical physics study, more protons will be aligned in the parallel direction, which is actually the lower energy state. Because particles, in fact, everybody will we always like to go into a low energy state. It is only when such is given excitation, is excited, that the whatever, if it is electron, it will now go to higher energy state. But under the application of field, an external magnetic field, all those disorientated dipoles spinning protons will now be aligned, either parallel or anti-parallel. Some will choose this orientation, while others will choose this orientation. But the ones that will be aligned in the parallel, usually more than the ones that will be aligned in the anti-parallel orientation. And for example, here we have one proton more aligned in the parallel position. So at the end of the day, the net magnetism, which is B1, the net magnetism of this object will now just be this one proton aligned in this, because this 3 will cancel this 3. Yeah, we have a one net magnetization vector up. So this is the equilibrium state of the hydrogen atom, of the atom, whatever it can be, any proton. So, but another thing we should note is the more the external field B naught, the more the external field applied, the more the difference between the states in this parallel orientation and the state in this anti-parallel orientation. For example, if you have our machine is at 0.3 about Tesla thereabout. So if our machine, which is at 0.3 Tesla, can have maybe say 20 million proton, more proton difference between this low energy state and this high energy state. That is, the difference between these two energy states, this one and this one, is 20 times 10 raised to power 16 20 million proton. That is 20 million protons will be aligned in the parallel direction. But if you now increase, if you have an MRI machine that is 1.5, I pray before the nearest picture we have a 1.5 Tesla MRI machine and even a 3.0 Tesla machine. So if you have a 1.5 Tesla machine, the number of protons, the difference between the number of protons in this direction and the number of protons in this direction will be increased. In fact, at 1 Tesla, we have about, this is just a hypothetical figure, number I've used. At 1 Tesla, you have about, at 2 Tesla, you have about 3 more protons in the parallel direction at 2 Tesla. At 3 Tesla, and so on and so forth, you have around 6 or so, and so on and so forth. So the number aligned, the difference between the number of protons aligned in this increases as the field strength, as the magnetic flux density, which we call the B naught, or just the magnetic density increases. So that is that about alignment. Let me quickly go to the screen again and see the. So an excess of hydrogen nuclei will line or parallel to B naught and create the NMV, that's the nuclear magnetic vector of the patient. So if you have a patient there, the excess hydrogen nuclei will line or parallel to B naught and create the nuclear magnetic vector of the patient. This is essentially the major contributing factor to whether we are going to have a better image or a low quality image. In fact, this is the reason why high field strength machines have advantage over low field strength machine, like the machine we have 0.32. You can't compare the contrast, keeping every other condition a constant. that of a 1.5 Tesla machine. It's just because of the abundance of the hydrogen nuclei that will line up parallel to the V naught external field. So that is the nuclei will also precess. We are going to go to that resonance and precession. When will the nuclei precess? As you have these nuclei, the hydrogen atom, even as they are spinning. Let me stop the share. And the hydrogen atoms, even as they are spinning about their axis. Let me make it clearer. Let's take Earth for example. This is our sun. This is the Earth. The Earth is inclined at an angle to the vertical. The Earth is inclined at an angle to the vertical. It rotates about its own axis. The Earth rotates about its own axis. And of course, because of that, that is why the Earth is also a magnet. In fact, anything rotating is a magnet because it is going to induce a magnetic moment. I just want to explain this, use this to differentiate between a spin and precession, because at times we get confused about these two things. When the Earth rotates about its own axis, that is the spin. The nuclide, the hydrogen atom, rotates about its own axis, just like we have for the Earth. This Earth, because of the gravitational attraction between the Earth and the sun, we will have the sun will try to draw the Earth with a magnetic, but because the Earth is spinning, it is going to be revolving around the sun. Of course, that gives us a year, and so on and so forth. Whereas the rotation of the Earth gives us day and night, as the case may be. So this is our precession now. The movement of the hydrogen atom of the Earth around the sun is what I can liken to the precession, whereas the rotation of the Earth about its own axis is actually the spinning. So for the hydrogen atom, when an applied magnetic field, external magnetic field is introduced, when we introduce an external magnetic field, the protons will now begin to precess. This is moving this way. Begin to precess. Another time this way. Another time you have it this way. Another time you have it this way. It will now begin to precess, forming. If we now join the locus of points, we are going to have a circle, depending on how you are viewing it. If you are viewing it from top, you're going to have a circle. But if you are viewing it from the side, it's going to be a kind of parabola. I mean, a kind of an ellipse. Parabola. So the hydrogen atom also precesses just because of the external field. Without the external field, there wouldn't be such precession. But if you now apply external field, they will now begin to precess even as they are rotating. They are precessing because of the external magnetic field. And the precession is not just straight. It will be tilted to an angle, just like we have for the Earth. It will be tilted to an angle theta. it will be tilted to an angle theta because of the magnetic field that has been applied. There is this game children play. They use something like a gyroscope. They spin it, and as something is spinning, it will be tilted to an angle. The spinning torso tilts at an angle as it rotates. It tilts at an angle because of gravity, but because it is spinning, it can't fall down. But as the speed, as the angular velocity reduces, the something begins to go at an angle until it finally falls when it stops. But if the something one can maintain the torso or the gyroscope spinning at such without loss of energy, it will continue till infinity. So that is what happens with our atoms, specifically our hydrogen atom, when we apply an external magnetic field. It begins to, after alignment, it now begins to precess. Okay, we are going to enjoy the more than 40 minutes. I actually prepared another Zoom meeting, but with the same password. I thought they're going to log us out, but I think that is not going to happen. So let me share a screen again. So due to the influence of the hydrogen nucleus wobbles spinning, the axis of the nucleus form a part known as the precessional path. So that's the path it is going to form. So this one looks like an elliptical orbit, but if you look from top, we are going to have something like this. This one, we are going to have something circular. And again, we are going to come to the term precessional frequency. So the speed at which the hydrogen precesses depends on the strength of B naught, and it is termed the precessional frequency. So for a precessional frequency of in a 1.5 Tesla machine, the magnetic field is 63.86. We are going to derive our own here. Our own is 0.32 Tesla. So how are we going to get the frequency of the machine we have in a UCH? We are going to get to that later. And again, one thing we should notice, the precessional part of the individual hydrogen nucleus is random. That is, all the hydrogen atoms, both the ones parallel and the ones anti-parallel, they are out of phase. That is their precession. I will be precessing, even though, sorry, look at this. Look at the precession of this. This one is oriented this way. The precession is going to follow this path. You're going to see something close to this. And this one is about horizontal. I mean, vertical. It is going to also be precessing at its own rate. I mean, it's going to be precessing given this locus. This one is also going to be precessing given this locus of points. They are all out of phase. They have their various phases, but one thing is common. They have the same precessional frequency. The only difference is that they are out of phase or randomly precessing. We need them to be in phase or for them to resonate. So that brings us to our third subtopic here. Our third point, we need to look at resonance. What do we mean for something to resonate? For something to be in a resonance? I believe one way or the other, we know the term resonance. But let me just bring you to children playing on the swing. If you have somebody on a swing and you want the swing, the amplitude of the swing to be very great, all you need to do is, as the person swings, when the person reaches one of the ends, either the front end or the back end, and a slight push at the angular frequency at the angular frequency of the swinging of the swing, you're going to have, it is going to add up to a very big swing. So that is a resonance. When you apply, when a frequency to a body a body undergoing circular motion or undergoing simple harmonic motion, when you apply a frequency such that the frequency you are applying is the same thing as the natural frequency of that body, or the frequency at which that body is oscillated, you are going to have the principle of resonance. So the something is going to resonate. So that will make it add up to have a bigger amplitude. So that is, this principle is very, very important in magnetic resonance. Another example of resonance is when we have, if one can actually crash a building, a skyscraper, if there is unity of purpose, if everybody begins, maybe on all the floors, everybody begins to match at a particular frequency. Everybody begins to match at a particular frequency. At a point in time, if of course, because buildings, they also vibrate. Though we see them as still, they actually vibrate. They actually vibrate, but at a very, very small level, with a very, very small amplitude. But if every person in that building begins to match at a rate of the natural vibration of the building, if it becomes so high so that the buildings can't manage the vibration, the building is going to collapse. This is, we've had some accidents in the past where bridges have collapsed due to resonance. In fact, when military men are marching on a bridge, they are advised to break their steps, because if they continue without their uniform step, the bridge might resonate and, of course, get destroyed. So we need the protons to be in phase or to resonate for us to have an appreciable principle for use in magnetic resonance. So when an object is exposed to oscillation, part of it that the frequency is close to blah blah blah, we have the natural frequency of the oscillation. We are going to have resonance. We have this Tacoma narrow bridge and failure, which is a very wonderful experience. Experience. We have that bridge, the bridge under resonance, it resonated, and look at the disruption that was caused much later. So resonance, the frequency of hydrogen proton in a 1.5 Tesla magnetic field can be found in RF bands, blah blah blah. So how do we make the precessing hydrogen bond? Precessing hydrogen atoms or precessing the protons to resonate. We do that by applying a radio frequency. Maybe in our next lecture, we are going to look at some of the components of the MRI machine. We have a magnet, the major magnet, which produces the major field. We have the gradient coils, which varies the field longitudinally, transversely, and the other plane, in the three planes, X, Y, Z plane. And we have the shim coils, which actually reduces the homogeneity along the major magnetic field. So we also have the coils, very, very important. So the coil, the RF coil, which is placed at the position we want to image, sends radio frequency coil. apply pulse during apply so that it's 90. So during resonance, the first thing that happens, how do we get resonance? Like I told you, for us to have resonance, we are going to apply RF pulse. Let me stop this share. For resonance to occur, we have to apply an electromagnetic pulse. It is not radioactive. I mean, it is not ionizing. We apply a non-ionizing RF pulse. The RF pulse is down in the electromagnetic spectrum, down in between the radio waves and the photons up there. What's it called? The gamma rays. RF pulse is in between them. So we have to apply an RF pulse, which is very close, whose frequency is very close to the frequency of the precessing atoms. If you apply an RF pulse whose frequency exactly matches the frequency of all the precessing hydrogen atom of the protons, let's use them protons. Of the protons, we are going to have the principle of resonance will come to play, because the frequency of the RF pulse exactly matches the frequency of the rotating proton. So that gives us a RF pulse. So the RF pulse will will make the resonancing particles, the precessing particles, to now begin to precess in phase. So instead of one precessing this way, another one precessing this way, that one precessing, they will all begin to precess at a particular direction. They will now be precessing in phase. That is the first thing that happens. Resonance is going to come in when you apply an RF pulse to the body. Let me continue with this share. So the hydrogen atom along with the RF magnetic field, and they now flip. So that's the second thing that happens. Initially, they will now look at the nuclear magnetic vector, will now flip towards the transverse plane. Initially, we have B naught, which is the external magnetic field, horizontally. This is just diagrammatic explanation of what we have. We have so many things that are going up here. This is just the net. This is just the net magnetization. This is just I'm sorry, I'm mixing it up. This is the external field. So if you now have, we also have a B1, which is due to the protons themselves. But this B naught is due to the B naught is due to the field, but we have small B1 due to the protons themselves. So we now apply this RF pulse. This B1, which also accompanies the nuclear magnetic vector of the protons themselves, will begin to flip after they have after they have been aligned in phase. They will now begin to flip towards the XY plane, that is towards the transverse direction. So the amount of flip that they undergo depends on the intensity of the radio frequency pulse. Intensity in terms of energy now, not in terms of course, it has to be at the frequency of the precessing protons, but also it is going to how and where they will flip to will depend on the strength of the pulse. Let me see this. By this law of induction, of course, the current will be. So before realization, let me briefly also throw more light on the resonance. Let me stop the share. Actually, what happens during resonance when you apply the external magnetic field? So many things happen. We have just described the summary. What actually happens? The first thing that actually happens is some of the protons in the parallel state, that is in the lower energy state, will now move towards the higher energy state, which is antiparallel. So at the end of the day, we are going to have the same number of protons aligned up and the same number of protons aligned down. So that is going to bring about a disequilibrium, which is actually what we want in MRI. So that when we remove the RF pulse, the process of relaxing, maybe the process of going back to their former state, and the process of defacing actually will give rise to the relaxation contents of T1 and T2 and the rest. So for resonance, this is the first thing that happens. The number of this thing down. So at the end of the day, we are going to have zero external magnetization. I mean zero net induced magnetization. But when we now apply, that's the first thing that will happen when you apply an RF pulse. Also, the RF pulse will now flip the protons, the NMM. Well, let me use a proton for better understanding. It will now flip the magnetization vector towards the vertical direction. I mean, towards the horizontal direction, depending on the strength of the RFM pulse. So they will now be aligned towards the towards the transverse plane. And as they have aligned, we should remember that it is still they are still processing the stuff in place. The the protons in place are still processing. So this nuclear magnetic vector will now shift towards the transverse plane. Then, depending on the strength and the time of application, it is either going to be maybe 30 degrees, 10 degrees, 15 degrees, 90 degrees, which is the maximum. At 90 degrees, all the magnetization will now be along the transverse plane. So we are not going to have any longitudinal magnetization again, M1. Longitudinal magnetization will not become zero because they have been aligned along the transverse plane. So we don't have any other component along the longitudinal direction, but everything is along the horizontal direction, that's the transverse plane, the XY plane. So we can also increase the RF pulse such that at the end of the day, we are going to have them aligned along this direction, 180 degrees. At that, M1 we now have minus M1. We no longer have transverse magnetization, MXY. If we continue, we're going to have 270. At that end, we're going to have maximum negative transverse magnetization. And if we continue, at the end, 360, we have that. So this is what happens. It depends on the amount of RF pulse that has been applied. So for MRI For MRI, there are so many things that happen. At times, we want to use a small RF pulse, a small angle, depending on the tissue of interest or what we want. At times, we want close to 90. At times, we get to 180, so that when something is going back to its equilibrium state after a removal of the RF pulse, we can have so many excellent image contrast based on their relaxation. So that brings us to the principle of relaxation. And before I continue, I don't. If you have any question at this point, we might entertain questions. You can just unmute yourself and ask your question.
Good morning, sir.
Yeah, good morning, Dr. Luashe.
Okay, I'm Dr. Yes, sir. Thank you, sir. I have a question, sir. When you got to the point of is that when we send the frequency wave, those protons they will align themselves. The one that are parallel in alignment and the one in anti-parallel alignment will now be equal.
Yes.
And what we're actually looking for is to achieve this equilibrium.
Yes.
I was thinking, sir, that if they are not equal, won't they cancel out? And the net negative, the net magnetic field we will have is going to be zero. And if that happens, how are you going to result into all the remaining ones that are flipping, giving this transverse direction? So I want more explanation on that, sir. Or maybe I didn't get that aspect.
Okay, no problem. I think I understand. For resonance, it is not a one-way process. There's something happens gradually, of course, in our own frame, very, 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 very fast, maybe 300, 200 milliseconds, and so on and so forth. It happens within a fraction of a second. When we first of all apply the RF pulse, the first thing that happens is we now begin to have more of the hydrogen, the proton will now be moving towards the anti-parallel state, that's the high energy state. And as that is happening, the net magnetization vector will now begin to shift from the initial position, because initially we have this. So as more begin to, I hope I'm not sure, as more begin to go down, this net nuclear magnetic vector will begin to shift towards the transverse direction. Begins to shift towards the transverse direction, that is towards the XY plane. Then at a point when you now have them being equal, that is when you now have this. You no longer have magnetization vector along the horizontal direction because they have all cancelled out. 3 here, 3 here. So mz equals m0. So what we now have is that we now have a maximum transverse magnetization, which will now lie along the XY plane. So depending on what you want. So this one is achieved when the pulse is at 90 degrees. But if you now continue, if we continue applying them, we now have some. We'll now be trying to go back to the Z. More will now be going down and down. So we now have them tilted towards this and so on and so forth. Till we now have the something again, MZ will now become the maximum. So what actually happens when you have it is 0 for longitudinal distance at the peak MXY, that is the transverse magnetization. We have the energy lost here. The magnetization loss along the horizontal, along the vertical axis will be gained in the transverse axis. I don't know whether it answers your question. The horizontal.
Yes, sir.
Okay.
Thank you, sir. You did, sir. I got it now. But from this, I have another question, sir. I'm sorry.
Okay, no
Thank
problem.
you, sir. So the radio frequency wave we are sending to disturb this their orientation,
Yes.
does it come with an angle, or is it the intensity of the energy that is changing their direction? I just want to know. I got the explanation that you explained now, that as they move, they cancel out, and that's when they come to line the transfer flip. I want to know what is responsible in the radio frequency pulse we are sending that is changing this. Is it the frequency? Is it the intensity, the energy they carry, or is there an angle being sent along with them? I just want to know that, sir. Thank you, sir.
Okay. That's actually handled by the machine mechanics. We have probably come to that later. We have what we call time of relaxation and time of echo. These are actually the machine dependent variables that we use to fire the radio frequency pulse. So this one is going to determine whether it is going to be 90, it's going to be 30, it is going to be 20, and so on and so forth. They have special number, because if to achieve 90 degrees, we might need to set TR at maybe 200 milliseconds and set TE at maybe 25 milliseconds, because time of repetition. So this time of repetition is usually greater than the time of echo. So these are the parameters that we, at our machine dependent, that we use in firing the. So when you just set all these things, it's something just the machine begins to automatically adjust itself, whether it's going to be 10 degrees, 15 degrees, and so on and so forth. So a whole lot of things actually do that to give us the angle at which is something we are going to flip the horizontal magnetization, the longitudinal magnetization towards the vertical plane. And again, the angle,
Okay.
the intensity, the rate at which is going to flip also depends on the external magnetic field. If the external magnetic field is high, then you have to apply a much stronger force to achieve a particular. For example, you have a 0.3 Tesla. The amount of energy it will use in going to 90 degrees will be much lesser than for a 2-3 Tesla machine. We need maybe for 45 degrees here, we might need some combinations here. But if you want a 3 Tesla, then you have a stronger RF pulse to achieve the same 45 degree pulse switching. I don't know whether.
Thank you, sir. I got it, sir.
Okay.
Thank you.
I think our time is almost up, but then it means at our next lecture we will continue from realization. Very, very, very important. Then we'll be looking at the concept of T1 decay, T2 decay, and then we continue to grasp more the concept of whether an image is going to be T1 weighted or T2 weighted or proton density weighted, and the likes. So at this point, I want to invite us for general questions. If anybody has any questions to ask, I think we are here together. Even some of us that we might provide answers to the questions. Dr. Henry Okoro, you have any question for us?
Yes, sir. Thank you very much, sir.
Dr. Eke, I can see you there. Any question from your experience?
No, sir.
Dr. Iretinko?
None. No, sir.
Okay. I hope the concept was we got at least some clearer understanding of some of these physics and content of resonance. But before our next lesson, before we go to realization, we might need to look at the components of MRI so that we begin to appreciate realizations the more. So thank you all for joining. I think our next class will be on Wednesday when we continue on. At least we have much more time on Wednesday. Oh, thank you very much.
Thank you, sir. How will we be able to get the slide, sir?
Of course, that was very easy. That was very simple. I'll send it on the page, on the WhatsApp page.
With the recording too, sir.
Okay, of course, you have everything on the recording and everything.
Thank you, sir.
You're welcome. Bye bye.
Thank you, sir.
Thank you.
Thank you. Bye.
Thank you.
Bye bye. Thanks.
Thank you, Chief. Thank you very much.
Welcome.